essentially, whenever we're converting from base 10 to some other base, the main thing you have to think about is how the pieces are going to fit together. Pieces, you kind of have to put in scare quotes. So let's say, for example, that I wanted to convert from 13 in base 10 to something. I don't know why I said sinks. Jeez. Been recording for too long, I can no longer spell. I couldn't spell before, but I'm getting worse at it now. Anyway, if we want to do this conversion, what we need to understand is essentially how many 6s we can fit into 13. Well, you would want 2 of them. And you can't get any bigger than 6 because the next thing up would be 36, and that's way too much for 13. So if you want to figure out what this is equal to, you would know that you have 2 6s. Then when you knock out 2 6s from 13, you'd be left with 1 single digit left. There's no 6s that can go into 1, but you can just take that 1 single digit. So you would end up with 2 1. I keep trying to spell sinks. So strange. 6, base 6. I should have picked more carefully when I chose at random. But the point is, you had 2 6s and 1 other that fit into 13 base 10. And that's sort of the idea for any conversion. It's just the problem is it's not always so obvious as with something that's small and manageable and near to the base itself. In general, if you want to run this conversion, what you have to do is start from your value base 10 and then identify the largest power of the new base that is still smaller than the value in base 10. So here, that happened to be 6 to the first power. If this was something like 130, then we'd have to go a little bit higher in order to get there. Actually, not that much higher because it'd be 36. But anyway, you'd have to keep going until you pass it, at which point you can't do anymore, so you go down. Where once you get to that highest point, you're going to use long division with that largest power, see how many times that goes in to that full number. That value is going to be your new digit, and if there's no remainder, then hey, you did it. You got really lucky. That does happen sometimes, that you have a thing that is a multiple of a power of the base, to be very specific, and there's not a ton of work, but usually that long division will leave a remainder. If there is a remainder, then you essentially repeat from the top with the remainder. So you take that value, take what's left over, check it again, and you keep running that until eventually you get down to the single digits, and there's where you're stuck. Kind of like what happened with that 1 there, except it takes a little bit longer to get to that point. Anyway, we'll see how this works with one more example. So for this example, we want to convert 3,444 in base 10 to a base 6 numeral. So what we need to do here, 6, I didn't realize I did that to myself. That's what I get for picking at random. Anyway, what we need to do here is identify the largest power of 6 that fits inside 3,444, where in this case, that would end up being 6 to the 4th, or 1,296. If we went one bigger, well, then we'd be getting a bit above 7,000, which is obviously a bit above 3,444, so we just have to work with that as the best we're going to get. So from there, we're going to take our value, 3,444, and long divide 1,296 into that. It's probably been a little while since you've done long division, but what we're going to do there is go over to our single digits, because hey, that's what we're trying to find here, where that value, the 1,200, will go into the 3,000 thing twice. We'll have 3,444 minus 2,592, which ends up being 852. It's a big remainder, but it's smaller than 1,296, so we have to go down 1 power, which is actually a good thing, because that's telling us how many of our 6 cubeds we're going to have, where, for reference, 6 cubed is 216, and then hopefully you know 36, 6, and 1. But then we're going to take that 852 remainder, long divide 216, that's only going to go in 3 times, and what we'll be left with is 204, where because that went in 3 times, that's our digit for the cubed terms. And we're going to take that 204, and now because it's smaller than 216, we're going to long divide by 36. We're going to take that 204, 36 goes into that at most 5 times for 180, we get 24, and then that 24 is going to have to be long divided by 6, power to the first, and thankfully that one does clear out because we have that 6 times 4 is 24, so we have a remainder of 0, and because our quotients are 2, 3, 5, and 4, we get that 3,444 in base 10 is equal to 2, 3, 5, 4 in base 6. Where, just to keep the fun going, base 6 is sometimes called centenary, and besides being used in Papua New Guinea, uniform numbers in men's college basketball are actually all 2-digit centenary numbers. The reason for that is because there's a nice hand signaling system that officials can use to call out the numbers of players as long as they keep them to those 2-digit values where each digit is below 6.
With a veteran move here. You can run the baseline and you got to remember that defensively.
Anyway, those are the main things we're going to see here for our 2 sections for the week. We're going to get some more practice with this stuff, especially this conversion with our worksheet as well. But next, we're going to move on into our 3rd section. We're going to get into some of the more algebraic type things we can do in these other bases, how the basic math looks when we're not just assuming that things happen around tens anymore, as well as a bit of work with that sort of arithmetic in terms of those old systems before moving on into chapter 5. But those are problems for people who are not in week 1, so I'll see you then.